this is the unit on matrices, the little mini unit we're going to do on matrices, calling it Unit X. And the first section, X.1, is matrix solutions to linear systems. So, question. What is a matrix? A matrix is essentially a rectangular array of numbers arranged in rows and columns. So that's basically what a matrix is, but probably better to show you eventually. But first, let's do kind of a problem from the past. Solve the following system of linear equations by the addition method, more commonly called the elimination method. I kind of like to refer to it as the addition method. Why? Because it involves the adding of the equations. So if you remember how to solve a system like this by the elimination method or the addition method, then perhaps you want to pause the video and try that right now. But so here we go. As I said already, this method involves adding the equations together, but it's not going to make any sense to do that unless the x's or the y's are opposites of each other, because when we add the equations together, we want either the x's or the y's to cancel out and kind of go away for a moment, okay? So here's what I'm going to choose to do. Since 2x and 5x do not add up to 0, they're not opposites, and negative 1y and positive 3y also do not add up to 0, that they're not opposites either, I have to make either the x's or the y's opposites. And the way you have to do that is by multiplying to one of the equations or both of the equations. And you have to kind of create opposites. Looking this system over, I see that it's going to be a little bit simpler to make the y's opposites. And all I have to do that is multiply to this equation in order to make this negative 1y into a negative 3y, because the opposite of positive 3y is negative 3y. So what should I multiply to this in order to make it negative 3y? Well, that's going to be 3. This equation, the second equation, does not have to change, but the first equation is getting multiplied by 3, and I mean like the entire first equation. So this 2x has to become a 6x, and this negative 2 has to become a negative 6, along with turning this negative 1y into a negative 3y. So that's my updated system. And now that these two terms are perfect opposites, I'm going to add these entire two equations together, like with them all being lined up and everything. So 6x plus 5x is going to be 11x. The y's cancel out as planned. And negative 6 plus 17 is positive 11. And now that I get this result, I can just solve for x real easy. by dividing both sides by 11 and getting x equals 1. This should seem at least a little familiar. Hopefully very familiar. And we are definitely not done yet, because not only do we have to solve for x, but we also have to solve for what? We have to solve for y also. You know, that's what it means to solve a system. We have to figure out what x equals, but also what y would equal at the same time. And the rest of the problem is a little less complicated, because once you know that x equals 1, you can use that to your advantage to figure out y. By plugging 1 in for x in one of these equations, doesn't matter which. I chose the first equation. You usually try to pick whichever one is a little less work or seems like it's going to be simpler. So I'm going to plug in 1 for x, and then just kind of take this through to the end, solving for y. And you know, no need to kind of go through all this process again. Eventually you end up with y equals 4, and that is your final answer, 1, 4. And so that's a review problem from earlier algebra classes. And then if you want to try this activity on your own at home, feel free. But let's jump ahead to a way more complicated, not way more, but a more complicated system that has 3 equations and a third variable in z. So now we're going to learn how to solve a system like this in unit x. So we will solve the system using matrices. A matrix gives a shortened way of writing systems of equations. The first step in solving a system of linear equations using matrices is to write the augmented matrix, which has a vertical bar separating the columns of the matrix into 2 groups. The coefficients of each variable are placed to the left of the vertical line, and the constants are placed to the right. So these are the constants, right? And the coefficients are the numbers in front of the variables, like the 2 and the 4, positive 1, negative 1, right? So those are the coefficients, and they're saying like a vertical bar is going to separate the coefficients from the constants. And if any variable is missing, the coefficient is naturally 0, of course. And so finally, let's kind of see exactly what we've been building up to and talking about. What is a matrix going to look like? So let's look at some examples of augmented matrices. So for this system of 3 equations, the augmented matrix would just have the coefficients and the constants, and that's it. So the first row would be just 3, positive 1, positive 2, and positive 31. The second row would be positive 1, positive 2, and positive 19. And the third row, what do you think the third row is going to be? That's right. Positive 1 for here, positive 3, positive 2, and positive 25. And notice how there's in these augmented matrices we have this vertical bar separating. It's kind of like where the equal signs are, separating the coefficients from the constants. Try this one on your own, remembering that if there's a missing term, like a missing variable and a missing term, then it has a placeholder of some kind. So pause the video and try number 2 on your own. Unpausing the video, this is what you should have got. 1, positive 2, negative 5, and then negative 19. And the placeholder here for this missing x term should be 0, and then just the coefficient here, positive 1, positive 3, and positive 9. we actually had a couple placeholder zeros in row 3 before we had a positive 1 for the z and a positive 4 over here. Okay, so taking a look at these two augmented matrices, right, which do you think would be the easier system to solve? You know, and again, we'd have to solve for x, we'd have to solve for y, and we'd have to solve for z. So which one of these matrices do you think would be easier to solve? Which one of these systems do you think would be easier to solve for all three variables? Hopefully it doesn't take you very long to figure out that I don't think there's any case to argue. It should be easier to solve this one. I mean, look, we already know that z equals 4. That's like 1/3 of the answer. So knowing that z equals 4 already, we could take this answer for z, plug it in for this equation in for z, and figure out y pretty easily. And then we would have what z equals, and we would also have what y equals. Using both of those, we could plug them into this equation, plugging in 4 for z, plugging in whatever we find out y equals in for y, and solving for x. So remember that process. Remember how this system is easy to solve for as you kind of like work it backwards, knowing that z equals 4, and then figuring out what y equals using that fact, and then finding out what x equals using both y and z. All right? Because we're about to kind of utilize that. But let's write the augmented matrix to our system here and then solve it. Final note on solving. We need to use row operations to make the matrix ready to be solved. When the matrix is ready, it will look to be in something called row echelon form. Row echelon form. Spoiler alert, looking like this. This is row echelon form. So I guess it's good to know that in advance. Our goal is to make the original matrix from our system to look like this, and therefore ready to be actually solved, like I just talked about doing. So here's our augmented matrix: 2, -1, +3, 3, 1, +4, -2, 7, +1, -2, -1, -4. So here we go. The first step I'm going to do is I'm going to switch R1 and R2. That obviously stands for row 1 and row 2. So row 1 and row 2 I'm going to switch, and R3, row 3, is going to stay as is. And my matrix will become that. 1, 4, -2, 7 becomes row 1. 2, -1, 3, 3 becomes, okay. And then row 3 stays as is. Now, I'm going to explain why I did that. Obviously, you can pause the video as needed to finish writing stuff down, but here I go. So, the only reason I actually switched row 1 and row 2 was because it is a very good thing to have our upper left-hand number be a 1. Okay? Maybe I'll follow up on that later as to like really why, but it's not, okay, it's not totally mandatory. It's not like it has to be a 1, but it makes your life a lot easier if your upper left-hand number, you know, the first number in row 1 is a 1. Again, it doesn't have to be, but if you see an opportunity, you know, I mean, if it's not already a 1, Like I bet you're going to do some examples where like there is already a 1, which is okay, great. But if the situation is as easy as, oh my gosh, I could just like switch a couple of rows, because you're totally allowed to do that. You're totally allowed to switch a couple of rows if you want to. And if switching a couple of rows will get you a 1 in the upper left-hand corner, then I think it's a step that's worth it. But that's all I wanted to do, is get a 1 right here. Okay? Now let me explain why that is, I guess, already. So I told you that my ultimate goal is to put my matrix in a row echelon form. What that basically means is I could have a 0 in these 3 positions. If I get a 0 in those 3 positions, I'll be able to solve for all my variables. Now, on a side note, there are other combinations of 3 zeros that would allow you to start solving for y or x, but as a rule, just to kind of keep things consistent, we're going to go with a 0 in these 3 spots and just go with that. So the first step we need to do in order is make a 0 in this spot and a 0 in this spot. We do that by doing these row operations. You know, just like back here, okay, where we essentially were looking to add rows together and make things drop out. That's what we're going to do. And look, here we needed to multiply in order to make some opposites before we added equations together to make a brand new equation. So that's what we're essentially going to do here. We're going to look to combine rows together in order to have zeros as a result, okay? So since I don't want to change row 1, you know, I do want to change row 2. I want this to become a 0, and I want this to become a 0. Row 1 is going to stay as is, okay? So row 1 can stay 1, 4, -2, 7. But I want to make a combination of 2 rows that will result in a 0 here, and then another combination of rows that will result here. So here's what we're going to do. We're going to have a combination of row 1 and row 2. I want to add row 1 and row 2 together, but if I do that, if I add these 2 together, I'm not going to get a 0 in this spot, I'm going to get a 3. So that means I need to do this. I need to do this row operation. I need to multiply this by a -2 to make it opposite of this 2. And then when I add them together, I'm going to make it a 0. But of course, it's got to be to like the entire row and the entire row. So -2, and this is where, you know what? This is where you might want to adopt a style where, you know, -2 times row 1, that'll make it into a -2, -8, +4, and a -14. Okay, kind of like write those off on the side or in a little bit of space. And then when you add these numbers with the row 2 numbers, you get those numbers. Because -2 times row 1 makes it -2, plus row 2 makes it 0. -2 times row 1, -8, plus -1 makes -9. -2 times this number in row 1 makes it +4, plus the number in row 2 makes it a 7. And then likewise, in this last part, negative 2 times, that's how we get negative 14. And then we add 3 to make it negative 11. So this brand new row 2 is the result of doing negative 2 times all of row 1 plus all of row 2. Okay? And now I need to do the same thing to make this number also be 0. Remember, this is our end goal for now. Well, it'll be like the end of one phase of our end goal. Okay. So here's what I want to do. I want to make a combination of row 1 and row 3. You know. And if I'm thinking of like adding row 1 and row 3, and again, I guess I'll get rid of that for a second. Row 1 plus row 3 is not going to make a 0 because 1 plus 1 is not 0. So if I were to multiply this row by negative 1, this would become a negative 1, and then it would add up with this number to become a 0. So this row operation is going to be negative 1 times row 1, and then we're going to add row 3. So basically here again, my brand new row 3 is going to be this. It's going to be the result of negative 1 times row 1 plus row 3. And again, if you want to kind of write this down, where that'll become a negative 1, negative 4, positive 2, and negative 7 when you multiply row 1 by negative 1. And then when you do this full row operations, negative 1 plus 1 will be 0, just like I planned. Negative 4 plus negative 2 will be negative 6. Positive 2 plus negative 1 will be positive 1. And negative 7 plus negative 4 will be negative 11. And so just like I kind of said, row 1 stayed the same, but my brand new row 2 was the result of all of this, and my brand new row 3 was the result of all of this. Now before I move on, I'm going to follow up on why it's good for that to be a 1. Like, remember how I switched row 1 and row 2 in the first place just to have a 1 right here? That was extra convenient because if you're using row 1 as a tool, you know, see how both of these row operations utilized row 1, right? This was a combination of row 1 and row 2, and this was a combination of row 1 and row 3. Okay? So it's very easy to create opposites in order to make these zeros if this number is a 1. You know, you can make positive 1 into anything, like super easy. You know, in this row operation, it was easy to make this 1 into a negative 2. In this row operation, it was very easy to make a 1 into a negative 1. So it's very easy to make the 1 into whatever you want in order to make it the opposite of whatever you need it to be the opposite of. Okay, and that's, you know, again, it's not necessary. You know, you can create these zeros even if this is not a 1 up here, but it's definitely a lot easier if it is. Now, what do we still have to do? Well, it looks like we need to make this spot a 0 still. Now, here's a very, very, very important teaching point in this process. You ready? When I go to make this spot a 0, I need to use a certain 2 rows to combine together. And the 2 rows I'm going to combine together, which, really quick by the way, I don't need to change row 1. Row 1 is going to stay as is. And you know what? I don't need to change row 2 either. But I am going to change row 3 because I need this to become a 0 at the end of the day. And like I was saying, you only are, it's only really going to work if you use a certain 2 rows to combine together. And it's got to be row 2 and row 3. In order to make this final 0, it's got to be a combination of rows 2 and 3. Well, I guess that was a little premature, but oh well. So if I'm going to be needing to make a combination of rows 2 and 3, it looks like I'm going to have to change both of the rows. You know what I mean? I can make this into a positive 18, this number, into a positive 18, and I can make this into a negative 18. And when I add those together, I will get that 0 that I want. So therefore, I'm going to multiply row 2 by negative 2, and I'm going to multiply row 3 by positive 3, and then I'm going to combine them together. Okay? Now notice this. Negative 2 times 0 is still 0. Positive 3 times 0 is still 0. When I add those together, I still have my 0. I didn't lose this 0 I just worked so hard to create. And that is the reason, people, why when you make your final 0, it's got to be using row 2 and row 3. Because if you use row 1 in your combination, you're probably going to lose that 0 while you're creating this 0. So anyway, moving on. Negative 2 times negative 9 gets me positive 18. 3 times negative 6 is negative 18. So adding those together, just like I planned, that's going to make that a 0. Negative 2 times 7 is negative 14. 3 times 1 is 3. And so when you add those together, you get negative 11. And finally, finishing, my multiplication of row 2 by negative 2, that makes this positive 22. And finishing multiplying row 3 by 3, this becomes negative 33, right? And when you add those together, you get negative 11. All right? So now I've transformed my matrix into this, which was one of my end goals, basically to get zeros in those spots. Because now what we're going to do is actually really pull the trigger on solving for x, y, and z. Okay, don't forget that this matrix of numbers represents equations that had x, y, and z in them. So at this point, once I get the zeros in those spots, I'm going to translate these rows in this matrix back into equations. 1x plus 4y minus 2z equals 7. And this equation would just become, 0x, so not even there, minus 9y plus 7z equals negative 11. And this equation is merely negative 11z equals negative 11. Okay? Look at this third equation. Just like we did before when it was like, hey, which one of these was easier to solve? And I even explained already how you would go about solving for z and then for y and then for x. We're about to do that right here. Can't you solve this for z like lickety-split? All you have to do is divide both sides by negative 11, and just like that, you know that z equals 1. That's 1/3 of our answer. Now we just need to find what y equals and also what x equals. Well, next, just like I said before, we're going to use, this equation to figure out y. Because if we know that z equals 1, we can plug it in for z, and that'll allow us the opportunity in this equation to solve for y. So like I just said, since now that we know that z equals 1, we can replace the z with 1. And that opens up the door, like I just said, to solve for y. Because 7 times 1 is 7. And then you can just finish solving this equation for y, and you get y equals 2. And now that you know that both z equals 1 and also that y equals 2, you can plug both of those into this purple equation, and that'll allow you to solve for the remaining variable, x. So z equals 1, so we're also going to plug it in there. Now that we know that y equals 2, we can plug it in there, and then just let this equation play itself out as we solve for the remaining missing variable of x. And ultimately we figure out that x equals 1. And there you have it, people. I know that was a very long problem, but it's finally over. And we now know that x equals 1, y equals 2, and z equals 1, which we can call an ordered triple. X, comma, y, comma, z. So the full solution is 1, comma, 2, comma, 1. In other words, x equals 1, y equals 2, and z equals 1. And that is that.